Welcome to the second lesson in simplifying radicals. This first part will be a quick recap of what we did in the last lesson. If you missed the last lesson, you're probably better off to watch that video as it goes in more detail, and I'm going to say slower than this one. So I just picked a couple of radicals here, and as you can see, hopefully you have the notes here. There's my long list of steps. Now, I'm not sure if that's helpful. Some students just like to have that process, and then if you're struggling with this, then I can see, okay, which step are you having problems with? So I will read them while I'm doing them here fairly quickly. Okay, so first step, we want to make sure that the radicand is not a perfect square or cube, okay? So whether it helps to have a list of those numbers handy, right? You'll see how that goes. Then what we need to do is separate the radicand into two factors that include the largest perfect square that divides evenly into the radicand. So this one will be root 9 times root 7. Okay, then we will rewrite the perfect square as its square root, and we also need to make sure that we remove that symbol, right? So root 9 is not the same as root 3. Root 9 is the same as 3, and there we are finished. Now, if we have a coefficient, which we do, okay, we're going to break that down into 36 times 5. And then we're going to bring this down. Okay, so as you can see over here, I kind of have this little setup for you. So the coefficient times the perfect square times the other factor. Then we break that down into the coefficient times the square root and the other factor. Just trying to get it back on the screen here. Then we multiply these two, and then we have a final answer of negative 24 root 5. So what do we want to do? Make sure that there isn't another perfect square or cube that divides evenly into this. 5's prime, so we're good. And then if we don't have an answer key, we check with our calculator to make sure that this decimal equivalent and this decimal equivalent is the same, because we have simplified, right? We haven't changed, we have simplified. So part 2 is just going to change our index. So yesterday, our last lesson, we worked just with the square roots. Now we're going to actually go beyond that, and there's no limit, but once you understand the pattern, it's really not that complicated. So I've got a list of perfect cubes for you there, and we looked at those in the first lesson as well. So we're going to follow these same steps, but now we're just going to switch our set of numbers. So it takes a little bit of practice, especially when I mix them up, to know when to use the perfect squares, perfect cubes, perfect powers of 4, perfect powers of 5, etc., etc. So 512, as soon as I slide it over, you can see is right here. So it is a perfect cube, and what that means then is that our final answer will not contain a radical at all. Okay, don't expect you to know what that is, but just make sure you can type in the cube root of 512 and you will end up with 832. So these questions demand one step that shows understanding before your final answer. Okay, cube root of 16. So remember, okay, so 4 is the largest, well, 16 is a perfect square, right? But this is cube, so now we have to use this set of numbers. You've always got to put that little index in there, okay? Because obviously it means something different, right? Because this is a perfect cube, it simplifies to that. Moving on to this one, the lovely fractions. Negative 2/3 times cube root of 27 times the cube root of 5. And then we'll put in that other step. Okay. Multiplying numerators, multiplying denominators, negative. I don't need to see this, by the way. I'm just going to put that there for you. I think what I'll do is I'll erase it. So negative 6/3 simplifies to negative 2. And this will work the same way, of course. You just have to get used to your calculator if you want to check the decimal equivalents, right? And there's no limit to the numbers, but I usually don't like to go too large because it's not necessary to be able to, remove large perfect cubes from things, okay? So cube root of 8 times the cube root of 5 plus or minus 5 times 2 cube root of 5, and then we have plus or minus 10 cube root of 5. So if you don't have practice with those perfect squares or the square roots that we were working on the other day, then this will be fairly simple, I think, and just take a little bit more practice. So I just have a couple more examples here, and I've included just some of the basic perfect powers of 4 and powers of 5, different sets of notes there. Okay, so this first one is a perfect power of 4, so it is plus or minus 2. So now we have to go 162. 16 doesn't divide evenly into it, but 81 does. Bring that negative down, that's part of our coefficient. 4 and another 4th root of 2. So this, you can look here, or you can type in the 4th root of 81, and we end up with that. Okay, moving on here. So looking again, so a little hint, right? Ends in a 5, ends in a 5, and that is the one that works. 5 times the 4th root of 625. Always make sure that this extends over the entirety of your number. 5 times 5, 4th root of 3, and then we have 25, 4th root of 3. And our last one is, so 5th root. Again, not too many numbers to play with. You can see, oops, no you can't. You can see they get quite large in a hurry. So obviously we don't have to worry about too much trial and error for that. 3 times the 5th root of 243 times the 5th root of 4. 3 times 3, 5th root of 4. So once again, typing in 3 times the 5th root of 972 will give us the same decimal equivalent as 9 times the 5th root of 4. This is just the simplified version of that. Thanks for watching.